Welcome to the next video in this series on forensic chemistry, and in this particular video we're going to be looking at distinguishing tests, those that are done at school versus those that are done in the forensic lab. Now basically at the school level a lot of our tests are destructive in nature. They're wet lab methods, okay? So if we were to break the types of tests up into destructive testing, so destructive testing are those that break or destroy the actual sample. And so examples of that would be when you react it with another when you react it with another chemical to see some type of reaction. So in previous videos we talked about reacting it with carbonates to determine whether the substance is a hydrocarbon, such as an alcohol, an acid, or alkene or alkane. Now in actual physically undergoing that process is destructive. So we're reacting them with other chemicals, and when doing that we're destroying the sample. Non-destructive methods are those that where you can do the test and actually have the original chemical intact. So an example of that type of test would be infrared spectroscopy, where the molecule is absorbing energy and it's just vibrating, but the actual chemical structure of the molecule is still intact, it hasn't changed. We could also say a lot of separation techniques can also be non-destructive as well, but here the separation techniques that we use usually involve a lot of solvents which can destroy the original material you're working with. So generally at a school-based method we employ a lot of destructive techniques. So let's have a look at a couple of those. So if we were going to be looking at hydrocarbons, what are the tests that we would do at a school level to identify those? And we've talked about those just recently. Well, we said we can react them with bromine water, okay, and see the rate of decolorization. We can react them with carbonates. We can test their acidity, okay, so if they're an alkanoic acid, we put an indicator in the solution to test their acidity. We can do it with a pH probe. pH probe would be non-destructive, so we could do pH tests. Of course, we've got the good old organic versus inorganic burn test, the charring test, so that's definitely destructive. Solubility tests, okay, so whether they're soluble or not, that can also affect their structure. So overall, wet lab techniques which are quite destructive in nature. But what about a forensic lab? Well, forensic lab, and if we put it down here, they will employ a lot of machines, right? A lot of machines that are large, expensive. They allow for faster analysis, smaller sample requirements, and so they can be anything from atomic absorption spectrometer, which is destructive, infrared spectrometer, NMR, etc. So there's a lot of different machines they can employ. We're going to be looking at the infrared spectrometer just quickly and at a basic level to show you how that a forensic chemist can identify whether it's an alkane, an alkene, or an alcohol, whereas in the school-based lab we would have to employ reaction with carbonates, the bromine water test, and the reaction with sodium. So I'm going to rub this off and we're going to look at how we would do it in the forensic lab with an infrared spectrometer. Alright, now we're going to look very quickly at the concept of infrared spectroscopy. So in this technique here, it's actually the absorbance of infrared radiation. Previously in the course we've looked at the atomic absorption spectrometer, which looked at the percentage absorbance of a particular wavelength of light by a molecule. So if we were looking at lead or we were looking at magnesium, we would use a specific wavelength emitted from a hollow cathode ray tube that is characteristic for the absorption values of the electrons in that particular atom. However, here what we're going to be doing is we're going to be talking about there's a range of wavelengths and frequencies over which we measure the percentage absorbance. And the fundamental concept here is that bonds absorb energy. So if we were to draw, let's say, hexane, or I should say hexene, 1, 2, 3, 4, 5, 6, Okay, so there's hexene. And we have different types of bonds in this molecule. So we have a carbon-hydrogen bond here. We have carbon-carbon bonds here. We have a hydrogen bonded to a carbon, which is then bonded to a double bond. And then we have, of course, a carbon-carbon double bond. So we have lots of different types of bond arrangements or associations there. And they will absorb energy at different wavelengths. Now down the bottom here, I've got something called the wave number. The wave number is the reciprocal of the wavelength, okay? So as the wavelength gets shorter and shorter and shorter, that means the wave number gets higher. In other words, the wave number is a measurement of the amount of waves in 1 centimetre. So here we have 3,000 waves in a centimetre, right? And so that means that has a wave number of 3,000. So the different bonds will absorb energies at different places, and when they do absorb it, they have what's called a stretch, okay? So if we can think of it sort of like this, that if we have, let's say the carbon and the hydrogen bond, I'm exaggerating here, if we think of it like a spring connected between the two, right, and those boxes represent the two atoms there, that when energy comes along, that energy can cause that spring to change in length, to vibrate. So as it absorbs the energy, it vibrates backwards and forwards and has a stretch. And so there's other different bond associations with that as well. The stretching is just one of them. Okay, we're not going to get into too much detail here, but imagine that bond absorbs energy, and when we get an absorption happening, we get a peak. And we have different peaks or different stretches, and you know, there's singlet stretches where there's one absorption, and there's a multi-peak absorption. And we have these areas that are characteristic for the types of bonds. So this here, very roughly drawn I might add, is the infrared spectra of hexene, right? Hex 1-ene. And we have characteristic regions within this that we look for that will tells us the type of bonds in this molecule. Okay, so here, that's the C double bond stretch. So the C double bond absorbs around about that region there, okay? It's not accurately drawn, but it's around about 1400. Then we have this here, which is around about 2900. That's the carbon-hydrogen stretch, just there, okay? And at 3100 is the carbon double bond hydrogen stretch, right? So we have different portions that absorb radiation, infrared radiation, and produces these characteristic stretches. So when we analyze the infrared spectra, we look in particular regions for particular bonds, and so we can analyze this and say, okay, well, it's got a double bond here. Here's the CC double bond. It's got a double bond connected to a hydrogen. There's the stretch there. And by putting that information together, we can come up with the structure of the molecule, okay? So that's how forensic chemists do it, very quick. They can repeat and do multiple trials, and it's non-destructive. Whereas in the lab, we have destructive techniques. All right, so we're going to look at another class of compounds now and see how we can detect for those versus the forensic lab. Okay, the other two types of compounds that we have to understand here is acids and bases. So in terms of the school lab, well, we use indicators. We can use pH probes. We can use reaction with carbonates. That'll produce CO2 gas. That indicates it's an acid, for example. So very wet lab destructive testing. In terms of the forensic lab, what do? Well, they would also use pH probes, but they can also use infrared spectrometry again, because what they do is they look for the C double bond OH stretch. Okay, so they can look for the area that absorbs the typical the carboxylic acid stretch there. So they will use machine analysis, whereas we tend to just only have sort of pH probes. What about salts? Well, in the school lab and in the forensic lab, in the school lab for salts, we do precipitation tests. Right? We do precipitates to find out the presence of a salt. In the forensic lab, they will be doing atomic absorption spectroscopy. Okay, so you can see a general trend here. The forensic labs are more machine-based, they're more non-destructive based, they're quicker, they're faster, they are more precise, they are also more sensitive than the methods that we use. Are very very laborious, very labour intensive, time consuming, wet lab destructive techniques, whereas in the forensic lab they have a lot more finesse. They can have a greater degree of sensitivity. They don't need as much. They can be working with samples that are, milligrams, nanograms, whereas we, of course, need to have a lot more sample to analyse. So hopefully that makes sense. Just a quick comparison of the two, and you should be able to explain and give examples of the advantages of forensic labs versus school labs. All right, see you in the next video.